First law of thermodynamics, when it is applied to an open system, has got tremendous applications all across industries. Using this law, you can predict what's the pressure drop across a nozzle, or how much is the energy required by this pump to pump the fluid out, or what's the heat transfer in the heat exchanger, or what's the amount of work produced by this turbine. In a nutshell, first law simply means conservation of energy, or it states that energy is getting transformed from one form to another form. We will understand how first law is applied for a thermodynamic system by analyzing a simple example, an example of piston cylinder arrangement. Here the cylinder has got some gas inside this, and assume there is no air leakage to the surrounding. So this is an example of closed system where mass doesn't change. Assume this gas is absorbing some heat Q from surrounding. Also assume that this gas is able to push this piston upwards due to high pressure of the gas. So this gas is doing some work on the piston with quantity W. There are two energy interactions for this gas. It is absorbing some heat and is also doing some work. So if we want to find out what is the change in energy of this gas, it will increase by a quantity Q because it is absorbing some energy, and it will decrease by a quantity W because it is losing some energy since it does some work. So you can write change in energy of the gas delta E as Q minus W. This is first law of thermodynamics for a closed system. And the same equation we can write in differential form like this, as rate of change of quantities per unit time. Now what we are going to do, we are going to open this system or open the cylinder like this. Now the system is no more closed, it is an open system now. The mass is continuously varying. It can have an inlet mass flow rate of this much quantity with particular pressure and particular velocity. Similarly, there will be an exit flow rate of this much quantity and pressure and velocity. Here also our objective is the same. We want to find out energy change of the gas or the system. But which gas? The gas is continuously flowing. You cannot define a particular gas over here. So before proceeding to the energy change calculation, we have to define a system first, a control volume, where we will do energy balance. Here the dotted line represents the control volume or the space where at which we will do our energy balance. Here you can see there are 4 energy interactions to the system in total. 2 energy interactions which is coming to the system and another 2 energy interactions which is leaving the system. So if you want to find out energy change of the system, you can sum energy transfer due to this 2 interaction and you can subtract energy transfer due to this 2 interaction. So for an open system, rate of increase of energy of the system will be like this. Heat absorbed minus work done plus energy transfer due to the incoming stream minus energy transfer due to the outgoing stream. The flow stream has got 3 components of energy: internal energy and kinetic energy. Finally is potential energy. Z represents the altitude of the flow stream. This equation is the first law of thermodynamics for the open system. But for an open system, the term W, the work done by the system, or in this case the gas, should be carefully examined. Here you can see gas is doing work to push the cylinder up, plus it is doing some work to eject the fluid out or to suck this fluid in. Or to maintain this flow, the gas has to do some work. And this kind of work which is required to maintain the flow is known as flow work. So the total work done by the system will be summation of WCV and flow work. WCV represents the visible work. In this case, work done by the gas on the piston. And we know flow work is the work required to eject the flow or suck this fluid in. And work required to eject this stream will be force at this area into velocity of the stream. And force is pressure into area. So you can represent flow work as this. And if you do some rearrangement to the equation by substituting the volumetric flow rate as mass flow into specific volume and by representing U plus PV as a new property, the enthalpy, the above equation will be simplified like this. This is a final and most useful form of first law of thermodynamics for an open system. Now we'll work out one interesting example using this equation. Here it is, a simple pump problem where fluid is getting pumped from point 1 to point 2. And we want to find out what's the energy required by this pump to perform this action. To find out that, we bring first law of thermodynamics for an open system into picture. And this is the equation. We can assume that everything is in steady state, so energy of the pump doesn't change with the time. So you can obviously put the first term as 0 because it is in steady state. And usually there won't be any heat transfer to the pump. So you can put that term also as 0. If cross-sectional areas of point 1 and point 2 are equal, then velocities at this point will be equal. So from this equation the velocity terms get cancelled out. You can also assume height difference between inlet and outlet are negligible. So the altitude term also get cancelled out. And finally what remains is this. Work done by the control volume or by the pump is mass flow rate into change in enthalpy. If you want to find out work required to the pump or to the control volume, then you have to just reverse the sign. Using the same approach, we can solve a lot of other energy transfer problems in industries. That is all about first law of thermodynamics for an open system. Thank you for watching the video.